Yeah, today's talk is about gold deposits associated with Cyanitic group intrusions in the Kurnalpi Terrane. And I'd like to start with a word about terminology. These deposits are orogenic gold deposits in the sense that they form during an orogeny. And I like to include them in the orogenic class, even though most people put intrusion-related deposits elsewhere. So I favour a subdivision of orogenic gold deposits into distal source deposits. These are the more common orogenic deposits in the Yilgarn, with a deeply sourced and unspecified source for the ore fluid, and proximal intrusion-related deposits, which are spatially associated with intrusions of mafic or syenitic group affinity, which are fairly common. Examples including Cyanides and Jundee as gold deposits associated with mafic group intrusions, and Wallaby and Karari, probably the most important presently, examples of deposits associated with syenitic group intrusions. That division of orogenic gold deposits is explained more fully in this recent publication on the Kalgoorlie-Kurnalpi Rift. One of the interesting things about the proximal intrusion-related gold deposits is that, in fact, 18% of deposits and 53% of gold ounces occur within 1 kilometre of a mafic group intrusion. In the Laverton district, there's a weaker but still significant association in space between syenitic group intrusions and 3.6% of deposits and 12.3% of gold ounces. Those figures for the Laverton district are strongly influenced, however, by Wallaby. So gold deposits associated with syenitic group intrusions, or SGEG deposits, they are spatially associated with syenitic group intrusions and hosted either by them or within their alteration aureole. That alteration aureole comprises high temperature oxidized hydrothermal alteration containing minerals like actinolite, biotite, and magnetite, which are similar in some ways to other intrusion-related deposits, including porphyry and IOCG deposits. But in the case of SGEG deposits, these alteration aureoles are generally low-grade or barren. The mineralization in these deposits is expressed as disseminated pyrite in mesothermal bleached alteration, which overprints the higher temperature alteration. But this disseminated pyrite commonly shows a relationship to millimetre scale to maybe a centimetre or two thick feldspathic biotite-rich or quartz carbonate veinlets. And there's a spatial zoning from high temperature proximal copper sulfides to distal carbonate sulfate lead zinc veins. Not that either of these achieve economic importance, but they are nevertheless interesting from an academic point of view. So the talk is based really on these 8 deposits listed in the top left. And the structure of the talk will be as follows. In the first part, I'll review the intrusion petrography, geochemistry, and the associated hydrothermal alteration. After that, I'll describe 4 specific examples of SGEG deposits and finish up with a model for the deposits. So this first map shows the Kalgoorlie-Kurnalpi Terrane with a distribution of syenitic intrusion samples subdivided into their respective supersuites as assigned by Cassidy et al. 2002. And some of the subsequent slides, particularly the geochemical plots, will make use of that database of Cassidy et al. So here we see in the eastern part of the Kurnalpi Terrane, there are numerous syenitic intrusions. These belong to the Wallaby and Ninnis supersuite. And in these, gold is associated with the Wallaby supersuite at Wallaby and the Ninnis supersuite at Tin Dog Flats. On the other western side of the rift, the Kalgoorlie Terrane, syenitic intrusions are rare or scarce. There's a better association here between gold and intrusions of the mafic group. The Mount Munga supersuite, shown in blue, actually straddles the boundary between the Kurnalpi and Kalgoorlie terranes. And also, as I hope to demonstrate in this talk, shows some intermediate characteristics between Cyanitic group and Mafic group intrusions. In the central Kurnalpi terrane, Cyanitic intrusions are again common, these belonging to the Eriinya, Claypan and Emu supersuites. But note that many Cyanitic intrusions, particularly in the central domain, these are the bright pink colours on the map, remain unclassified. In the central domain, there are fewer gold deposits and they're smaller in size. So the intrusions, Cyanitic intrusions, and the associated gold, without saying that they're completely contemporaneous, they both were formed during basin inversion when the margins of the rift were reactivated during the period 2675 to 2620 million years. I'll point out that, I don't know, I hope this is working, the Yilgarn syenite just south of Karari is classified as Claypan supersuite, but my, my view is that the intrusions at Karari are actually part of the Mount Munga suite, and I will hope to convince you of that as we go along. Looking at more detail in the central Kurnalpi terrane, I've shown the 8 deposits that we're looking at in the labels, coloured by their supersuite affiliation. And make note that the north and south of the terrane, where I've labelled deeper erosion, comprise granites and granite gneisses uplifted from mid-crustal levels. And the cyanitic intrusions in these areas tend to be quite large and appear as outcrops on this map. The down-thrown Kurnalpi greenstone basin, by contrast, contains very small intrusions, and many of these are porphyritic high-level intrusions. There's a possible association between the intrusions and regional faults and late-stage basins, but the intrusions are not confined to the late-stage basins. And one of the major themes of this talk will be what role exactly does the cyanitic intrusions play in the formation of the gold deposits spatially associated with them. These next 2 slides both come from the down-thrown Kalgoorlie-Kurnalpi greenstones and show what the coarse-grained cyanites look like. These are both examples of the Emu supersuite from Cement Well on the left and Handorf Well on the right. The cyanites comprise less than 5% quartz and dominated by coarse-grained phenocrysts of alkali feldspar. These alkali feldspar phenocrysts are commonly closely packed, almost resembling a cumulate-like texture. And sodic pyroxene and amphibole being hydrous, interstitial to the alkali feldspar phenocrysts, indicating late crystallization, as you would expect from an anhydrous A-type granite. On the right, the Handorf Well cyanite contains abundant microgranitoid xenoliths, and these indicate a mantle source component for the cyanites, and probably also indicate limited fractionation. Going back to the left-hand photograph, this pipe-like structure outlines the alkali feldspar phenocryst very well with the interstitial biotite, and it's very tempting to interpret this pipe-like structure as a gas or volatile escape structure. When we look at the cyanitic intrusions in the vicinity of the gold deposits, we see quite a different sort of rock. This is a high-level porphyritic and porphyry intrusions, again with low modal quartz and dominated by alkali feldspar phenocrysts. Some of these are closely packed, and occasionally we see trachytic textures well developed as well. But of particular note in these examples is that the porphyries have phenocrysts of biotite and amphibole, indicating that those minerals, those hydrous minerals, are crystallizing relatively early and suggesting or indicating a hydrous nature for these intrusions. While the textural preservation in the intrusions is fantastic, microscopic examination indicates that the mineralogy of the intrusions has been extensively modified by subsolidus processes. And finally, as illustrated in the upper left photograph, which is a photograph of one of the open pits at Butcher Well, we see lamprifiers and cyanites very closely associated in space, and this is very common in all the. This is common to all the SGEG deposits, even though lamprifiers are not included in the syenitic group. Looking at whole rock geochemistry now, these various plots show both the syenitic group and the mafic group samples on various plots. The TAS, or total alkali silica diagram on the right, illustrates well that both the syenitic and mafic groups have an extended silica range going back to about 50–55% silica. And this is in stark contrast to the volumetrically dominant granites in the Eastern Goldfields, the low calcium and high calcium groups, which plot in the high silica range up here with in the upper 60s to lower 70% silica. However, the mafic group intrusions are distinguished from the syenitic group intrusions by lower potassium, and the syenitic group intrusions plot in the high potassium calc-alkaline field and shoshenite field on this K2O versus silica plot. Note in the upper two plots there is overlap between the syenitic group and the mafic group. This is particularly evident for the Emu and Mount Munga supersuites. All suites, including the low calcium and high calcium groups, converge towards the high silica end of these plots. And the fact that these syenitic group samples are clustering in a distinctive trend gives us some confidence that the whole rock chemistry has not been changed drastically at the analytical sample scale, despite the fact that many of these samples were taken from gold deposits and their environs. Nevertheless, we should be interested in the immobile elements to confirm our classification of the syenitic group intrusions. And this Pierce plot, zirconium over titanium versus niobium over yttrium, shows that the syenitic group intrusions straddle the subalkaline to alkaline division, and also that the 4 red squares, which are taken from the Karari gold deposit, plot there with the Mount Munga supersuite. The syenitic group intrusions have high field strength element concentrations, in common with the mafic group, especially the Wallaby supersuite, which is shown as these smaller brown symbols. They were the immobile incompatible elements, and this slide addresses the immobile compatible elements, chromium, vanadium, and cobalt. It shows that the syenitic group intrusions have high chrome, vanadium, and cobalt, though not as high as the mafic group intrusions. Nevertheless, the elevated chrome in these intrusions, the syenitic group intrusions that is, suggests the mantle source component supporting the observation of the microgranitoid xenoliths at Handorf Bore. And combined with the high thorium, zirconium, and niobium, suggests a metasomatized mantle component for the syenitic group magma, or possibly crustal contamination of a mantle-derived magma. More plots involving immobile elements here indicate that the Wallaby supersuite, the brown triangles, extends to very high thorium and zirconium. Whereas the Mount Munga suite, again, we're showing the Karari intrusions coincident with them, has very high vanadium and chromium. These two plots address fertility indicators published by Bob Laux for copper-gold mineralisation associated with intrusions. And the top plot shows that the syenitic intrusions have an adiabatic composition with high strontium over yttrium, indicating amphivolfractionation and a hydrous magma. So many of the syenitic group intrusions plot in the fertile field on that plot, and as do many of the Mafic Group intrusions with the green outline here. And they're also coincident with fertile intrusions associated with alkalic porphyry copper plus or minus gold deposits in the Lachlan Fold Belt of New South Wales and in British Columbia. Another important fertility indicator is the oxidation level, and the syenitic group intrusions have among the highest Fe2 over Fe2O3 over FeO ratios in the Kalgoorlie-Kurnalpi Rift, higher than the Mafic Group intrusions. And that high oxidation fugacity is supported by the mineral assemblage clinopyroxene magnetite titanite, which is typical of unaltered syenitic intrusions. So just recapping on what I've said so far, magmas fertile for gold copper mineralisation, including alkali porphyry deposits, that they are oxidised, hydrous, and have a metasomatized mantle source component. And in the Kalgoorlie-Kurnalpi Rift, these parameters are best displayed by the Mafic Group and the Syenitic Group magmas. For the Syenitic Group, the Wallaby and Mount Munga supersuites appear to be most fertile. This is not said with any great degree of confidence because the work really hasn't been done yet, but there is an empirical spatial relationship between Wallaby supersuite and Wallaby gold, and Mount Munga supersuite and Karari gold. Also, these supersuites show some of the most extreme chemistry within the Syenitic group, though not necessarily in the same direction. And I'll just reiterate the fact that the Mount Munga supersuite samples straddle the eastern margin of the Kalgoorlie terrane, and perhaps not coincidentally shows intermediate or transitional geochemistry between the Syenitic and Mafic groups. Moving on now to hydrothermal alteration, and there's an extended hydrothermal alteration sequence associated with these deposits and intrusions. The earliest alteration is ferruginous alteration, which comprises iron-rich minerals like actinolite, chlorite, and magnetite. They have some similarities, at least qualitatively, to early high-temperature alteration at some IOCG deposits, where they are interpreted as products of an early high-temperature saline fluid of magmatic hydrothermal origin. And I think the same can be said about the ferruginous alteration associated with syenitic intrusions. However, in the case of the SGEG deposits, these ferruginous alteration halos are generally barren or low grade. They're overprinted by a bleaching or sodic alteration, which is nicely demonstrated by the central slide, or central photograph, taken from drill core at Butcher Well. This ferruginous alteration has also been seen in association with some Mafic Group intrusions, as for example at Admiral Hill, and the three lower photographs are from Admiral Hill, where that alteration is associated with, so far, uneconomic copper-gold mineralisation. Another high-temperature alteration facies is potassic alteration, dominated by K-rich minerals, particularly biotite, but also in these assemblages we find albite, magnetite, and sporadically pyrite and chalcopyrite. So this assemblage has some similarities to early magmatic hydrothermal alteration in many porphyry deposits, where again, they're attributed to early high temperature saline fluid of magmatic hydrothermal origin. Potassic alteration in SGEG deposits are gold poor, but they do host low-grade copper mineralisation at Karari. The lower slide shows a transition from the potassic alteration, which is dark brown, to the later bleaching or sodic alteration, where that magnetite, magnetite and biotite have been destroyed and replaced by new minerals. The potassic alteration is also associated with Mafic Group intrusions at Admiral Hill. The next alteration type is bleaching or sodic alteration, which is dominated by feldspar, dolomite, rutile, and pyrite. Notice that the iron in all these minerals is Fe2+ variety, and this is indicating a lower oxygen fugacity than the higher temperature alteration styles. And although many of the sodic alteration zones are coloured by dusty hematite, that hematite represents a volumetrically very small amount of the alteration assemblage, and in my mind at least is due to some sort of later oxidized fluid flushing through the system, and therefore not related to the bleaching and sodic alteration. In fact, this sample from Whirling Dervish is sodic altered, and with no hematite. As I say here, the origin in terms of the hydrothermal fluid for this style of alteration is still ambiguous, but it's also present in some mafic group intrusions, the wall rocks thereof. In fact, the sodic alteration is a major host for gold at Navajo Chief and Janet Ivy in the Vinduli camp, both associated with mafic group intrusions. That's in the Kalgoorlie terrain. The final alteration event in these deposits is represented by quartz, dolomite, pyrite, plus or minus muscovite in brittle fracture arrays that overprint the bleached rock. These are controlled by brittle faults and probably formed at mesothermal temperatures or even lower, and they are host to most of the high-grade gold at deposits like Wallaby and Golden Delicious. So reviewing the alteration now, SGEG deposits are associated with high temperature alteration of the ferruginous or potassic varieties caused by magmatic hydrothermal fluid. They're generally barren to low grade in the case of SGEG deposits, but they are iron rich and therefore act as a potential chemical trap for later gold bearing fluids by destabilizing gold bisulfide complexes. The later mesothermal alteration, the bleaching and the silicification are associated with faults and brittle fracture arrays, and the origin of these is ambiguous or contested, but typically these host the moderate to high grade gold grades in the SGEG deposits. I'm now going to describe the 4 deposits listed at the bottom of the slide as individual case studies. Before I do that, I'll show the distribution of those deposits highlighted in white labels, white text labels, on a gravity image. And it's quite evident that SGEG deposits, as well as other deposits, are located on or at the margins of first and second order positive gravity anomalies. Presumably, these gravity anomalies indicate thicker mafic ultramafic greenstones. And the deposits show an association, particularly with north-south and northwest trending gravity lineaments. So this effectively establishes our first targeting criteria, that the SGEG deposits occur on the margins of positive gravity anomalies. Here's Wallaby, which is obviously the most completely described deposit in the literature. It comprises a central cluster of syenitic intrusions dated at 2664 million years and surrounded by a pipe-like shell of magnetite-bearing alteration, actinolite magnetite or actinolite magnetite calcite epidote, depending on whose publication you read. John Miller also described this deposit and observed radial calcite magnetite vein arrays centered on the syenitic intrusion and proposed magmatic hydrothermal models for these. Calcite magnetite veins are also present at Karari and at Safari Bore, I think it is, to the south in the southern Laverton tectonic zone, where it's a major host to gold mineralization. The bleached or reddened alteration is also present at Wallaby, but this hasn't been well described or emphasised in the literature. The emphasis at Wallaby is on the shallow north dipping brittle faults shown in various colours here, which contain the high-grade gold. The origin of the deposits remains contentious. Roxalia proposed a distal source or deeply sourced ore fluid for the Wallaby high-grade gold. And that was based on a difference of about 40 million years between the age of the intrusions and the age of the mineralisation. The age of the mineralisation in this case was determined using uranium-lead systematics in phosphate minerals. On the other hand, Andreas Müller and co-workers dispute this age difference and propose a model, propose a magmatic hydrothermal model based on their molybdenite age, which was coincident with the intrusion age. And they also noted the potential for phosphate minerals to be reset by younger events due to dissolution and recrystallization. That bullseye anomaly is iconic in terms of Wallaby. It's a very stark exploration target, and other Syenite-associated gold deposits in the Laverton terrane, such as Jupiter and Cameron Well, have similar strong bullseye anomalies. So that would be targeting criteria number 2. But we should be a bit wary in this instance because of the propensity or potential for the magnetite to be destroyed by younger alteration. And in that case, if that younger alteration, which is more closely related to gold, is extensive, then that bullseye anomaly will be destroyed or at least weakened. Another way of targeting SGEG deposits is through bottom of hole geochemistry. And these maps show the bottom of hole geochemistry in the Laverton district and arranged in terms of elevated molybdenum plus tungsten plus bismuth, which pretty well identifies syenitic and other granitic intrusions. That parameter is often interpreted as the product of an oxidized fluid, but molybdenum, tungsten and bismuth are also enriched in the granites themselves. The other component or parameter is arsenic plus antimony, and where this is elevated, it identifies high strain zones such as shears and faults. So at Wallaby, we have a case where there is a juxtaposition of these oxidized and reduced signatures shown in red and green respectively. But notice also that Jupiter and Cameron Well are solely oxidized signatures, and whether that signature reflects the composition of the intrusions at those deposits, the syenitic intrusions, or their associated high temperature magnetite bearing alteration remains to be determined. Models proposed for mixing of hydrothermal and reduced fluids as a mechanism for developing gold mineralization really don't stack up in my mind. I think that that association is better explained by this diagram in the lower left, which illustrates strain partitioning around an intrusion. So it's a very common gold setting in the Yilgarn and for orogenic gold deposits globally. And the intrusion will be oxidized and have elevated molybdenum, bismuth and tungsten, whereas the encompassing shear zones will have elevated arsenic and antimony. Moving on now to the next deposit, this is Golden Delicious, located a few kilometres northeast of Sunrise Dam. The magnetic image on the left shows the extent of a monzodiorite porphyry intrusion. That's the red cross-hatching. And that's the dominant host for gold at Golden Delicious. But notice that the magnetic anomaly extends well beyond the limits of the porphyry. And that magnetic anomaly is caused by magnetite-bearing ferruginous alteration, both in the porphyry and in the wall rocks of the intrusion. So this shows the ferruginous alteration in the porphyry, and this shows relics of ferruginous alteration in the enclosing mafics or andesites. Notice that the ferruginous alteration has been overprinted by regional carbonate alteration, thus constraining the ferruginous alteration to a fairly early stage. And we note that there's no bullseye magnetic anomaly here at Golden Delicious. It's quite a linear anomaly. Thus, we might need to modify targeting criteria number 2 to include linear magnetic anomalies as well as bullseye anomalies. The 4 pictures of drill core in the center of the slide illustrate the progressive bleaching or alteration of the monzodiorite porphyry via carbonate alteration of the ferromagnesium minerals. And importantly, we note that the ferromagnesium minerals, the amphiboles in the monzodiorite porphyry, are forming phenocrysts, indicating relatively early crystallization and a hydrous magma. And that would be our targeting criteria number 4, hydrous magmas indicated in the field by phenocrysts of amphibole and or biotite. Leaving Golden Delicious and moving on to Karari, which is in the Carosue Dam camp, there are several SGEG deposits in the Carosue Dam camp. On the left, we have a geological map, and on the right, we have an aeromagnetic image. The cyanitic intrusions and associated gold deposits in the Carosue Dam camp are in this mustard-coloured volcanoclastic sedimentary basin. These are felspar-rich quartz pore sediments, probably derived from the intrusions themselves. On the right-hand side, we see this volcanoclastic basin outlined in the black dotted line. And within that, we see a number of relatively modest linear magnetic anomalies. And these tend to be coincident with the syenitic intrusions. Gold is associated with north-northwest trunking faults within this basin, and with the north-south faults which cluster around the narrow neck between the 2 granites on either side of the volcanoclastic belt. So at Carosue Dam, the magnetic anomalies associated with syenitic intrusions are not only weak, but relatively modest, which requires another modification to our targeting criteria number 2. Geochemistry and alteration are zoned on a quite unique and spectacular scale at Carosue Dam. We have a 20 by 3 kilometre zoned hydrothermal system centred on these syenitic intrusions. The map on the left shows the intrusions with the crosses and their high temperature or their alteration aureoles comprising metassic and sodic alteration in the pink and brown colours. Surrounding that central core, there's a zone of muscovite alteration and then distal chlorite alteration. Distal chlorite alteration may be related to metamorphism or regional carbonate alteration, whereas the muscovite alteration zone is barren and it has apparently formed by regional strain partitioning around the rheologically strong intrusions and their associated alteration. Bottom of hole gold in the Carosue Dam basin is shown in this slide here, and the gold anomalies are quite tightly constrained around the deposits themselves. But this allows us to construct criteria number 5, which is a kilometre scale hydrothermal system with proximal biotite or amphibole alteration and sodic alteration. Looking at bottom of hole geochemistry at Karari, or Carosue Dam, I beg your pardon, we see that some elements such as copper, molybdenum and bismuth and tungsten are concentrated in that central belt of intrusions and proximal alteration, whereas zinc and arsenic are progressively enriched in the more distal portions of the system, with arsenic peaking in the muscovite alteration zone. So arsenic and high strain go together here as well. A progressive enrichment of various pathfinder elements, such as copper, bismuth, molybdenum, tungsten, silver, zinc, and arsenic, provides a sequential vector to gold mineralization, as illustrated in this graphic in the lower left. So targeting criteria number 6 would be district scale alteration zoning and sequential enrichment of pathfinder elements. The next slide shows a map of Karari, probably the premier gold deposit in the Carosue Dam camp. The open pit exposed the Eastern intrusive complex, comprising syenitic porphyry, monzonite and lamprifier intrusions. On the left, we have barren footwall sedimentary sequence, and gold is found in this central domain, which I've called the central mineralized domain, where volcanoclastic sediments dominate, but have been intruded by syenitic and monzonite porphyry intrusions. The maps on the right show the distribution of gold, which is also close to the distribution of tungsten and arsenic in the central mineralized zone, and the enrichment of virtually all other pathfinder elements, copper, moly, lead, bismuth, zinc, tellurium, antimony, in the Eastern intrusive complex. The photograph on the lower left shows a view looking south at this wall of the open pit here, and differentiates the Eastern intrusive complex from the broad zone of potassic alteration in the volcanoclastic sediments, and immediately in the footwall of the hanging wall fault, which separates the two, is this slightly reddish zone of sodic alteration or bleaching, which contains the gold. This hanging wall fault is interpreted as a reverse fault, uplifting the Eastern intrusive complex with respect to the central mineralized domain, and suggests that we might find similar intrusive complex material beneath the mineralization in the central mineralized domain. This is what the ore looks like at Karari, bleached but reddened by hematite dust, with relics of the former high temperature biotite or potassic alteration. The pyrite is predominantly disseminated and forms small veinlets as well. And in detail, these are spatially rated to millimetre to perhaps a centimetre scale veinlets and stringers of feldspar veins, biotite veins, biotite pyrite veinlets, as shown in here. And there are also some of these are fairly rare, grey cherty quartz pyrite veins. For an ore petrologist, this material is rather boring. Pyrite is by far the dominant sulfide. Tellurites haven't been observed, and other sulfides such as galena and sphalerite, chalcopyrite are really quite rare. At McAuliffe Well, which is another deposit north of Karari and Carosue Dam, we have a circular cyanide intrusion surrounded by a magnetic annulus of biotite and magnetite of hydrothermal origin. At McAuliffe Bore, we've got a regolith-hosted gold deposit at Dingo down here, but the main basement-hosted mineralisation of interest is in this northeast trending brittle fault that cuts through the syenite and into the surrounding mafic wall rocks. This is a detailed map from the exploration company's report, which shows the fault offsetting and cutting the syenitic intrusion. And a graphic log on the right here shows that the golds, sadly uneconomic at this stage, are associated with these brittle fracture arrays, similar to the ones described at Wallaby. And they occur in a background of variously altered bleached monzonite or cyanide. Notice importantly in this least altered sample, the amphibole and biotite is forming phenocrysts, again indicating a hydrous magma. So I move on now to a couple of rather speculative models. I've said already on a couple of occasions that the origin of the gold ore fluid in these SGEG deposits is ambiguous. So I'll present two alternative models here. The first acknowledges a magmatic hydrothermal ore fluid for the gold. And in this scenario, we recognize high temperature magnetite stable alteration. This is the ferruginous alteration and the potassic alteration. And at these high temperatures in oxidized fluid, we would expect gold to be present in the chloride as a chloride complex. Whereas the mesothermal stage, the ore fluid has cooled. So the high temperature fluid has cooled to temperatures of 250 to 350 degrees. And that's accompanied by a decrease in the fluid oxygen fugacity in acknowledgement of the Fe2 plus bearing species that comprise that bleached sodic alteration assemblage. So the combination of decreasing temperature and decreasing oxygen fugacity would lead to the deposition of gold. This is that vertical blue arrow there. And at the same time, coincident with cooling, the sulfur dioxide in the magmatic hydrothermal fluid potentially would be converted to HS- through hydrolysis. And then the high-grade gold ore in the brittle fracture zones, they may have been deposited by, boiling or phase separation, and thus removal of HTS from the vapor phase, deposition of gold in the residual alkaline fluid. So the alternative model is this one here, which incorporates an unspecified deep source for the mesothermal gold mineralization. In this model, the high temperature potassic and ferruginous alteration around the syenitic intrusions is exactly as it was for model 1, magmatic hydrothermal fluid. But the mesothermal stage acknowledges a deep-seated distal source for the gold fluid, where the gold is transported as bisulfide complexes. During the mesothermal stage, gold in the pyritic feldspathic rocks may have been deposited then by reaction with the iron-rich wall rocks, the ferruginous and potassic alteration. And again, the high-grade gold ore in the fine-grained pyritic silicified lodes caused by phase separation. So here's a general non-genetic model for SGEG deposits, based largely on my experience at Carosue Dam. The top graphic is a plan view emphasizing the north-south faults, the central core of syenitic intrusions, and their aureoles of high temperature, ferruginous, and potassic alteration, outboard of which we find muscovite alteration. The cross section shows a deeply tapping fault or structure necessary to provide a conduit for magmas coming from the upper mantle, the metasomatized mantle source, and allowing emplacement of the Cyanitic and Mafic Group magmas. Early high temperature ferruginous and potassic alteration caused by magmatic hydrothermal fluids surrounds these intrusions. Magnetites present, but gold not in these high temperature alteration aureoles. The mesothermal alteration, which does contain the gold, is in volumetrically smaller domains of sodic alteration or bleaching, and the higher grade gold in the later brittle fracture arrays associated with silicification and pyritization. Okay, so that is the guts of the talk, and I'll finish up with a couple of slides which enumerate the conclusions. Firstly, SGEG gold deposits are spatially associated with syenitic group intrusions and their hydrothermally altered wall rock aureoles. They are proximal intrusion-related gold deposits in my subdivision of the orogenic class, but that doesn't necessarily imply a magmatic hydrothermal ore fluid. The Kurnalpi Terrane contains numerous syenitic group intrusions, of which the Wallaby and Mount Munga supersuites appear to be the most prospective for associated gold, but there's more work required in that space. The mantle-sourced syenitic magmas have the required hydrous and oxidized nature of magmas responsible for copper-gold mineralization. Compare both the composition and nature of the syenitic intrusions with those associated with Phanerozoic alkalic porphyry copper-gold systems. The syenitic intrusions are associated with high temperature potassic and ferruginous alteration, commonly magnetite bearing. And these alteration types are attributed to a magmatic hydrothermal fluid derived from the syenitic intrusions. Copper mineralization is poorly developed in these deposits, but mesothermal gold associated with some syenitic intrusions is hosted in pyritic bleached feldspathic host rocks that overprint the high temperature alteration. And these in turn are cut by biotite pyrite stringers and the silicified pyritic fracture arrays. And it's the latter which contain the highest gold grades in the SGEG deposits. And as I said before, the origin of the gold mineralization is uncertain. Is the ore fluid magmatic hydrothermal fluid or a deep unspecified source? Targeting criteria for SGEG deposits. First of all, gravity. The deposits are found on the margins of first and second order positive gravity anomalies. Magnetics. The deposits are often identified by strong positive bullseye anomalies, but we also have to be aware that some of the more subtle linear magnetic anomalies may represent syenitic intrusions and their alteration aureoles. Targeting criteria number 3 is the juxtaposition of oxidized or granite-related and reduced high strain lithologies and geochemistry. This is not fluid mixing. It's a reflection of the strain partitioning around rheologically strong syenitic group intrusions. The syenitic intrusions have a hydrous nature indicated by amphibole and biotite phenocrysts, at least where they've been placed in shallow crustal levels and where the gold deposits are associated. Some, Carosue Dam at least, is identified via a kilometre scale hydrothermal alteration system with proximal potassic biotite alteration and sodic alteration and distal muscovite and chlorite. And finally, there's a district scale zoning of pathfinder element enrichment so that we can follow each of these elements from a distal location to the gold itself. So that completes the talk.